All right, so now that we have the data set, we've looked at the distributions of our single variables, let's actually try fitting the analysis of variance. So we can do it a couple ways, right, with a one-way ANOVA. We could either do it through fit y by x or through fit model. We saw last time that fit model is a little more general and we can use it for more things, so let's actually do it through that. When we start checking assumptions, we're actually going to go back to fit y by x for this particular type of analysis because it gives us some interesting ways to look at the residuals and also the normality assumptions. Let's start with fit model. And for this, it's going to be fairly simple, right? We're just fitting job category as our factor, and we're trying to predict the individual's SCI scores. So just load those in there, and we can leave everything else pretty much the same. We don't have to change anything else. And go ahead and run that. Now again, the place to look, if your parameter estimates were expanded, you can just close those for analysis of variance models. We typically don't look at the parameter estimates because what we're really interested in is the effect of our variables. The fact that JMP parameterizes in the way it does is fine, and if we need to interpret them, you can always expand that. But remember, effect tests are really where you're looking for the effect of your factor, right? It's actually handling the fact that it's constraining the model to have certain parameters and all that stuff. But the effect tests are really where we're looking. And in this case, we can see right away that we do have some effect here, right? These means are not from the same population. We have evidence that they actually differ. Or in the terms of the model, or sorry, in terms of the data, individuals of different skill levels are actually rating the organization differently in terms of their safety. To get an idea of what that difference is, again, under our drop-down for the factor, we can request the plot, which gives us a quick way to look at really what that difference is or where that difference is occurring. Now one thing that's really handy for these, the way that JMP scales these variables has to do with the range of your data. Unlike, let's say, SPSS, which what it will do is actually scale the graph to just fit the data points. So what you tend to get when you plot things in SPSS or by default is your effects look really huge because it scales it just to have the data points fitting into the graph. Whereas JMP will scale it to be a little bit wider, so effects look small. So rescaling is actually a really important thing, not important, but useful thing to get an idea of really what's different from each other because they look pretty similar here. So I don't know if I mentioned this before, but the little hand here, if you see it sort of left and right here, that actually lets you just move the scale up and down. But if you move it to the bottom of the scale, it turns to that downward facing hand, and you can just drag out the scale. I don't know if I mentioned that before, but it's handy to resize these things. And let me actually just make this bigger too. So just looking at this, we can see right away that the difference really is that the job supervisors here, they're the ones that are really rating the organization as being safer. And this might make sense. They're actually doing a job that is probably safer, and so the types of things that they experience in their workplace environment is less dangerous, so they're rating it as less dangerous. You might also notice that the error bars here are different, and that should be expected, right? We have a lot more unskilled workers, so the estimate of that mean is actually going to be more precise. Right? So remember, these error bars are representing the mean squared error divided by the square root of the sample size, or the root of the mean squared error over the root of the sample size. So if our unskilled workers are more represented in our data set, the ability for us to estimate that mean is greater, and so that error bar is going to be smaller. Right? So that shouldn't throw you off as something that's wrong. That's just it reflecting what state of nature you have or what evidence you have about the actual means. But we haven't actually compared any means statistically, right? We've just looked at the fact that they differ. We know that some mean is different from some other mean, but we haven't looked at where that difference actually is occurring. So one thing that we can do right off the bat, and this is sort of just coverage that we did last time, are these two different ways of actually computing the simple test, right? The simple pairwise comparisons. We can do it with a student's t, which actually doesn't correct for alpha, so it's just going to perform all the tests at our overall, whatever alpha rate it's going to be set at, so 0.05. Or we can hold down shift and select it to actually do a different significance level. But if we were actually running this comparison, we may not have real a priori hypotheses about what differs, so I might just run a 2 keys. Might be the way to do it. And if we do this, we get an indication that really the supervisors are the only category differing from the others, right? In this little connecting lines report, or connecting letters, we see supervisors get an A, the others get a B. So these are essentially, as far as we're concerned, having the same mean. We don't have evidence that skilled and unskilled laborers are differing at all in their perceptions of safety, whereas supervisors are differing from the other two. Now, in this design, we really have different ways we can think about it. So supervisors are really a different category, right, than the skilled and unskilled workers. Like they're a different class of employee. They're actually doing different jobs. Whereas the skilled and unskilled may also be working on the floor. They may share qualities in common that would contribute to their particular ratings. So one thing, and actually this is what, when I found this data set, it was originally in the context of, was doing a contrast to really tap this difference. Right now we're just comparing each mean to each other, but we might think that comparing the supervisors against the mean or the average of the unskilled and the skilled workers would be an interesting comparison. Right? They differ in terms of maybe where they work in the plant or things like this. So we can actually structure our analysis to really reflect that difference, or to do a comparison that gives us a result that may give us something interesting we can talk about, more so than just saying that supervisors differ from skilled and unskilled. So if you remember from last time, if we go to the drop-down and actually request the contrast, so least squares mean contrast here, we can set up a contrast that actually does that comparison for us, right? Comparing the supervisors against the average of the skilled and unskilled workers. And if you remember, all we have to do for that is just give a plus for the supervisors and give minuses for the skilled and unskilled. And JMP is going to handle for us the constraints, right, of the contrast. So it's going to keep the absolute value, the sum at 0 and the sum of the absolute value of the weights at 2, right? So it actually is standardized. So if we run this, right, we actually get that specific comparison, right? So the average of the 2 down here versus the supervisor. And that might be something we would actually be interested in even before the fact. So if you were doing contrasts of this sort, it's probably something you're not even going to consider correcting for in terms of alpha, because you really knew before the fact that maybe this was an interesting comparison, something that you wanted to look at. And again, if you go down here, you get all the relevant information. It's giving you the F statistic, right? Your numerator and denominator degrees of freedom, sums of squares. And so if you're reporting this in a journal, you would actually say something like you performed the specific contrast comparing the average of those two groups against the mean, or against the mean of the supervisors, and you would report the F statistic with the degrees of freedom. So again, in this way, contrasts, and Mark's made this point too, really give you a way to structure your analyses to really talk about the things you're interested in talking about. So there's no reason to run extra analyses that don't really reflect your hypotheses. Right? Always sort of think about things and how can you use your statistics to argue whatever point you're trying to make. If you're trying to make the point that the difference here, the critical difference, is not the skilled and unskilled or this dimension, but rather where they're working, right? So what job they're performing, then you can do this analysis and sort of make that point more specifically and directed. Okay, yeah?
You're presuming the difference between the supervised and then the skilled and unskilled from the beginning, right? That's why you're applying the contrast in the weight that you're giving.
Sort of. I mean, you don't have to even have a priori predictions about this. Basically, I'm saying just take the average of these two and compare it to the supervisors. I'm saying really that the dimension that separates them would be their supervisory role, because these are both essentially subordinates, and this is a supervisor maybe. Maybe I'm not understanding your question totally.
It's just like running the Tukey compares them all
to each other.
With the contrast, you're saying which groups you want to
compare to which other groups.
Yeah, you're
exactly.
One to the supervisor and
exactly.
To the other two.
Yeah.
So you're sort of presuming that there's going to be this difference between the two groups, right?
I mean, there may not have been. We may have actually not detected that effect. But yeah, I mean, it can be, I guess.
This would have to be a prediction a priori.
Yeah. Yeah. I mean, it might be a prediction because you think that there's, And I mean, this particular analysis would be, this would be the same as if we just went to our data set and recoded and gave, let's say, the roles of subordinate or supervisor and ran the analysis that way. So that's essentially what it's doing, right? It's just grouping these two categories, lumping them together, and then comparing it to the supervisors. Yeah. But it gives you a way to do this in the analysis rather than going through the trouble of restructuring your data, really. And as you get to even more complicated, contrasts, this is going to be a much more handy way to do it, just because it's direct and quick. Right. But again, these contrast weights, right, they're just telling you, or they're telling JMP which categories to consider when it's comparing one thing against the other. They're weights, right, but what they're really doing is just saying these two categories count the same, and we're going to put them into one group and compare it to the other. So it's not as though you're really doing anything special that you couldn't have done before the fact. Your data is not suggesting the contrast weights so much as your analytic sort of need, if that helps. Okay, so We did all of this on these contrasts before really checking assumptions. Really the strategy that would be optimal, or something that you would probably want to do first, is actually look into whether the ANOVA is appropriate for these data. Right? Do you have violations that would suggest that you need to do something different? Because there's nothing worse than finding an effect and then finding out your model really is wildly inappropriate, and then having to go back and tell your advisor it didn't actually work out or something like that. Not always fun. So the thing I would do here is just go into your save columns, and like we had before, save your residuals. Now, for the analysis of variance as we're doing it here, the one-way analysis of variance with no covariance, it turns out that our residuals are going to be, at least our interpretation of and the checking of assumptions with the residuals, will be no different than actually if we just check the variable themselves. Because if you think about what the model is doing, of course, the model is just saying every group we're estimating a mean for, and then the residuals are just the deviations from that group mean. So imagine if we were to, instead of considering the residuals, just considered the actual points in our data set, right? And we looked at those points differing from their own group. It's going to be the same thing because all the model's doing is shifting around where those means are and trying to predict what they actually mean. So the residuals are going to have the same value as just the difference between the group and its own mean to begin with, without any model. Now when we get into analysis of covariance or any more complicated analysis, especially non-orthogonal designs, that's not always going to be the case. So the general rule is just stick with using the residuals, because really that's what the model assumptions are relevant to. It's that the residuals have a normal distribution and that the residuals have equal variance across your groups. It just happens to be that if you're in a pinch and you can't save the residuals, you can just look at the single distributions of your groups and see if they're normal or equal variant. But let's stick with the residuals because it's just a more general way, and we'll stick with it for later. So now that we have our residuals, let's again remember that the assumptions of the model are normality of error and homogeneity of error. So we can look at these residuals split up by group to see if they're equal variant and if they're normal. So the quickest way to do this is if we go into Analyze and fit y by x. And what we're going to be predicting or plotting is actually those residuals, right? So the residual for the SCI score. And we're going to split it up by job category. So actually let's put that in as a factor. And notice that it's going to do a one-way here, or it says it's going to do a one-way analysis. That's fine for us. Now, if you were to actually perform an ANOVA on the residuals, just intuitively remember that what it means is they're going to all be zero by definition, right? The sum of the residuals in any group is going to be zero. So we can't actually perform any real analysis looking for mean differences. The only thing we're concerned about with these residuals is their distribution. Are they normal? And are they as variant, right? So are individuals as far from their group mean in each category, right? So are unskilled workers as far on average from their group mean as skilled and supervisors? And just looking at these, we can see there is some difference, right? The supervisors are tending to give more similar ratings to their safety, right? So their residuals are closer to this 0 point, right, to their group mean, than the unskilled and the skilled workers. But to get a little...
Fewer of them, they cap out at 20, as opposed to the others, they cap out at 30.
Right, right, and they're a little bit more spread here. To get a handle on this actually with some quantitative measure, we can just go to the drop-down, and as we've seen before, like we did in regression, we can just select unequal variances. And what this is going to do for us is actually to test several different ones for whether the variances are equal in each group. And these are the tests we've seen before, the O'Briens, the Brown-Forsyth, the Levine, and the Bartlett. And what they're doing for us, of course, are different things. So the O'Briens doing a different analysis than the Brown-Forsyth and the Levines, but they're all telling you essentially the same thing, right? Are the variances equal? And the test here, if it's not significant like we found before, is saying that we don't have evidence they differ. So these are tests for if there's evidence in the population that the variance is different, or that individuals will be different in their residuals in the population. And here we have none of these coming up statistically significant. Typically they'll agree, especially if other assumptions are met. But in this case, we really don't have any evidence or any need to worry about unequal variances. Essentially, in that respect, our ANOVA model is just fine. We don't have any reason to do anything more complicated. Okay, so that's for variances. Now for the normality of our error, what we did in the past was actually go to Analyze and Distribution and actually split the file using that by variable to get different distribution plots. Now in the one way here, or in the fit y by x, we can actually get one piece of this puzzle, the normal quantile plot. We can actually get it for all of our groups at the same time. So if you go to normal quantile, and select either of these, just differs on which axis it puts your actual scores, you can get, as we've seen in the past, that QQ plot, right? So the plot that plots how far an individual actually was, and by how far we would expect them to be from the center given a normal distribution. And this is a little bit more messy, so I typically like to split them up just because you can see things better. But right away you can see essentially they're all following the same trajectory. They're falling along the fit line, right, of what you would expect under normality. There's nothing hugely off here. But this is a little messy of a way to look at it, so I probably wouldn't do it this way. If you had to do it quickly, this could be something you can do. But the way I would recommend is actually closing this. So we're done with the homogeneity of variance assumption. We're upholding it. It's fine. What I would do is go into distribution, so the single variable distribution, and we're going to be looking at the residuals, but we don't want to look at the residuals overall, right? Because what we're concerned with is whether the groups, within the groups themselves, the error is normally distributed. And so if we look at them overall, it's a little different of a picture than if we look at them broken down by group. And so the way we can get JMP to do that is using that by section. And in all analyses and all platforms, by does the same thing. What by will do is split your file, essentially treat your file as if it only had each level of these categories for each analysis it does. So like we saw before, putting it in here will do for the first category, unskilled laborers, it will do the distribution plot, and then for the skilled, and then for the supervisors. So it's actually going to separate the file for us and produce different outputs. So if we run that, we get the actual single distribution plots, and they're all looking a little bit skewed, which we might expect because when we looked at the overall distribution for all people, right, it was already skewed, so that got reflected equally about in our single distributions here. But for each of these, and if we hold down Command, we could actually do it all at once. For each of these, we can request that normal quantile plot, the thing that we just request in the other platform. And it gives us a way to look at these separately in a little bit more, with a little bit more clarity, or at least to see it a little more clearly. And looking at the QQ plots again is, it takes some time before you really can see. This one looks a little less normal. This one looks a little bit even more off. This one surprisingly looks okay except for the bottom points. But as we did in regression, we can actually fit continuous distributions to each of these and run that goodness of fit test to see if we have really evidence that we've departed from our normality. And one thing I'll note here is that each of our groups has a lot of individuals, so 91, 51, and then 448. So our power to detect departures from normality is actually quite high, right? So we should just be aware of the fact that we're going to be able to detect even minor departures from a normal error distribution. So let's do it and then look at our results and sort of think about them. So again, under continuous fit, and I'm holding down Command first before I click it, or Control if you're on a PC. Continuous fit and fit in normal. And then still holding down Command under that fitted normal, request that goodness of fit test. And what you're almost certainly going to find in each of these groups is that we have evidence that those errors are not normally distributed. So this is a departure that we're going to find out tomorrow is not as troubling as if we were to find out the variances were unequal. It's of course not great for us to find out that we have violations, but in this case we're a little bit better off, especially because the variances are equal and we have fairly large sample sizes. So the nice thing about the central limit theorem is if we have more people, it tends to correct things for us. We have to worry less about deviations from distributional assumptions with large samples. But anyway, at this point, you pretty much have evidence that these distributions aren't particularly normal. And even just looking at the single distributions, that was pretty evident. But given our sample sizes and our non-heterogeneous variance, as we'll see, that's not terribly troubling at this point. Okay, so is everyone fairly comfortable with checking normality here and what we did here, splitting it up by groups, right? All right. So that's actually all we're going to do with this data set. For the simplest analysis, that's all you would really have to do. Check the homogeneity of variance with those three groups and check the normality of those three groups. And given how large of an effect we really have here, I mean, these are pretty massive Fs, and especially in this analysis, large F. Even with violations, you know, as we'll see tomorrow, our error rate isn't inflated so much that we would have to really be concerned that these are just spurious. If we had very marginally significant results, so if you're getting p-values at a 0.05, 0.04, I might be a little more suspicious, at least for myself, that my particular analysis may be flawed, and I might do something non-parametric just to follow up, make sure that when I'm going to tell the world about this, I'm not giving out results that won't replicate or aren't real at all. But in this particular case, with small violations and fairly robust or small p-values, I wouldn't be particularly concerned with it. Okay, so let's close out of that one and not save. I don't know where I put that folder. There it is. The next one let's look at is fitness. This is our two-way ANOVA. So let me tell you a little bit about this data set. This is, I got this from somewhere. I think it's actually a real data set. So it's looking at individuals' heart rate after 6 minutes of exercise, broken down by gender, so males and females, and also this control versus runners. So runners are classified as individuals who typically run more than 15 miles a week. So people who are running that much. And I guess controls, they listed as people who live a generally sedentary lifestyle. So whatever that means. If less than 15 miles or fewer than 15 miles a week is sedentary, then 15.
Okay.
Either way, it's kind of bad. I don't think.
Well, 15 is like, that's feasible. Like, you could imagine that someone could run 15 miles a week.
Yeah.
50 is like, that's like
People do it.
All right, so we have the control group and the Kevin group. So the question of interest, right, was after 6 minutes of running, would we find differences in their heart rate, essentially? So I think it's 6 minutes after, was it after a treadmill or 6 minutes after stopping running on a treadmill? Whatever it was some measure of cardiovascular health is what they were trying to get at with this particular data set. Again, the thing to do, let's actually run just a distribution, looking at our groups in gender and heart rate, just to get an idea of what the distributions of our data are. We have equal numbers of runners and controls, which is nice, equal numbers of males and females. In a minute, we're going to look to see if we have equivalent numbers in each cell, so each combination of those two. And if we look at heart rate here, we see we have not a terrible distribution. That's a little bit, I don't know if that's a little bit skewed maybe. Someone here, 200 heart rate after 6 minutes. But nothing here that would make us really be concerned about, wild miscalculations or outliers. If we had somebody down here at like 30 or someone at like 275, we might worry that someone misentered something or someone died in our study. I don't know. Who knows? Actually, so there was an ad on the radio that, so now they have to do this reporting thing with all medications or all prescriptions, that they have to tell everything in a plain voice, I guess. This is why on prescription drug commercials, like there's scenery going on, but they're still telling you about how it's going to like cause colon issues or something. The person's like playing baseball, Anyway, there was one, I forget what it was for, but they had this 10-second piece about how deaths were reported in clinical trials, but it was unclear whether it was related to the prescription, which I thought was really humorous. But people died, but we're not sure. They might have died anyway.
It's unclear, but then let us just put it out anyway.
Yeah. So, yeah. Anyway. So no one here looks like they died. Everyone seems like they're doing okay. And our distribution is roughly normalish here, not terribly concerning. No outliers to speak of. The next thing I would do, just to make sure that we have the right numbers in each combination of cells, so each treatment, which is just the intersection of our factors. So a treatment is just any combination of these two. Actually, sorry, not distribution. Do analyze fit y by x. So what we're going to get here is that mosaic plot. Remember, that's the way to graph nominal against nominal. So I'm going to take group and stick it on the x and gender as the y. Either way is fine. It's just going to plot the same thing, just flipped. And it's going to do for us a contingency analysis and give us this nice mosaic table. And from our mosaic plot, we can see, right, that we have equivalent numbers in every treatment, so every combination of our two factors. Another thing that's nice about the mosaic plots, right, is it gives us our marginal sums. So right here is the male and female difference, and we can see right here easily that they're equal. And these two, the widths of these two bins here, also tell us our marginals for the group membership, so we can see that they're equivalent there as well. So mosaic plots are really neat ways of displaying things quickly. And like I said before, when we get to chi-squares, and we'll probably have some time tomorrow to talk about contingency analysis, you would look down here to see if you have evidence, if you were sampling these people randomly, whether the distribution in these groups differed by categories. So for example, if we're actually randomly sampling people, whether there were more males than females who were runners or sedentary, something like that, we can see if those two factors are independent. But we'll get to that later. So for now, everything looks fine. We have equal numbers in all of our cells, which is great for us, especially if we have any violations. This is going to protect us a little bit, or protect the F test from being sort of unduly influenced by any violations that are out there. So we can close that. Now the first thing is, let's go ahead and fit the full model, right? So we have to do that through the fit model platform, because now we're looking at a two-way analysis of variance, right? We actually have that interaction term that we have to fit. We're not just fitting the effect of each factor separately. We're now considering them together, and also whether they interact, right? Whether the effect of one factor depends on the level you're in of the other. So the quick way I showed you last time to get these into the full factorial is just select your two factors, go down to macros, and actually select full factorial. And what that'll do is just build you the model with each factor effect plus the interaction term, so the group by gender. And what we're trying to predict here, we're trying to see if there's differences in, is the heart rate. So I'm just going to select that. And everything else we can just leave as it already is. Now notice that what it did for us is expand the parameter estimates and not the effect tests. In this particular type of analysis, when we only have two levels of each group, you'll see actually these values are going to be the same. And I have to believe that's why JMP expands out the parameter estimates, but I'm not entirely sure what the purpose is. As a rule, I would just minimize those, because you're almost never going to be talking about the particular parameter estimates you obtained, especially because, as Mark rightly pointed out, if you do an analysis, the same analysis, but add another cell, so we had people who were even more than runners, we'll call them extremist, whatever, who run 50 miles a day, our parameter estimates are going to change, but the effect of any particular mean comparison won't. So having these parameter estimates, interpreting really the estimates of these parameters is contingent on the grand mean, whereas the effect tests are not, in a sense. They're actually testing whether there's some effect, amongst the means, rather than this analysis, which is really testing, is this estimate here different from 0, essentially. So in any case, minimize the parameter estimates, and let's think about the effect tests in general. Now we're going to hold off on looking at the assumptions for a second, because we have to do something a little bit tricky to get JMP to do them for us. So let's actually just look at the effect tests here first and see what we're dealing with. We see already that we have a group by gender interaction, which is indicating to us, of course, that the effect of group depends, or the effect of group depends on which gender you are. So depending on which gender, how being a runner or control affects your heart rate is differing somehow. We don't have an idea of how it's differing yet, but we know that it differs somehow, or we have evidence that it does. Looking down the line here, we also see that gender has some effect. That is, average heart rate for the genders averaging over group differ in some way. So we have some marginal effect there. Marginal, of course, meaning at the margins, an average effect. In group here, we also see we have some difference. So averaging over gender, we see that groups, control versus runners, are also differing. So in heart rate, those groups actually differ after 6 minutes, which all this is pretty expected for us. Now the easiest way with a two-variable plot, or two-factor ANOVA, to really see everything is just do that two-way interaction plot. So if we go to the drop-down for the interaction and request the plot, we can see really quickly all the pieces at once. So we can see not only what the effect is of being a runner versus a control, and what the effect of gender is, but we can also look at the interaction all at once. Now, as we'll see when we get to three-way interactions, we're going to have to build this up a little more in a more complicated way. We'll have to get the effects for each factor separately, and then think about really what's happening in the interaction. But of course, you could get the single factor plots here if you just wanted to look at the average difference between controls and runners, and the average difference between males and females. But again, in this two-way interaction, this is easily viewed in the interaction plot. And we can see here that they're almost parallel, right? So parallel in an interaction plot implies that the interaction is 0, right? But these are slightly non-parallel, but ever so slightly. So if we drag this up and expand it out, we can sort of exaggerate where that interaction is. But basically what it looks like is that the difference between being a runner or a control for females is actually larger than if you're a male, right? So this difference here and this difference here are different, right? So that's actually the definition of an interaction, and you can say it easily in a 2-factor setting with 2 levels of each factor. It's just the difference of the differences is statistically different. So yeah, the effect of being a runner essentially is bigger for females than males, is what that interaction is telling us, right? And we can do the drop down here and actually get that Tukey if we want to compare all the means. We have so many people in this particular data set that we have enough power to really say that everyone's different from everyone else. So ABCD here. So the nice thing about this is we can say pretty confidently that all of these means are different, right? But that interaction is telling you something kind of special, that the difference here between controls and runners, it is there in the population for males, but it's just larger for females, right? It's actually a bigger difference than it is for males. So for whatever reason, that's females maybe get more of a benefit from being runners than males do. There's plenty of confounding variables here. Females may, because our classification was running more than 15 miles, we don't know, maybe females who fell into the runner category actually ran an average that was larger than males. So males maybe ran an average of 20 miles in the runner category, whereas females ran 25. There are plenty of things that could account for this other than just cardiovascular differences amongst the genders, which is of course an issue with using intact categories in general. So of course we didn't randomize people to gender, we had to observe that in nature, and things differ that we're unaware of, right, when we don't randomize people to conditions. So for pseudo-independent variables like gender, we always have this issue that people just may differ already when they come into our groups. But in any case, we certainly can say that there is some difference here. Accounting for what it is gets to be a little more complicated. But there is some difference between how being a runner affects males and females. Now, before we get to testing assumptions, I want to show you quickly that this group by gender interaction here is nothing more than really the contrast that detects or picks up on that difference of differences, right? Because all contrasts are really are little detectors. You set them up to detect differences within your data set or amongst your means in such a way that they tap whatever it is you're trying to tap. And so Mark showed a real simple way of actually getting an interaction contrast, which was if you have the contrast for the main effects of your groupings, you just can multiply the contrast down and get the interaction contrast. So let's actually write these out with a pen that works. So if we imagine that we're ignoring the factorial structure of our data set, and we just think of these as 4 groups. So we have at the highest level males and females, and then within males and females, we have controls and runners. Right? We can think about the contrasts that are actually tapping both our main effects and our interaction. So for the main effect, let's talk about the main effect of being, let's say, of gender. Right? The main effect of that is really just a comparison of these cells and these cells, right? So if we were to come up with a contrast that taps that difference, we're supplying the negatives to one side and the positives to another. And these are unstandardized contrasts. We could just divide everything by 2 and get the ones that JMP is going to produce. Right, but off the bat, that's actually what's going to tap the gender comparison. And we can actually do this just to confirm for ourselves that that's actually right. Let me minimize some of these and go to the drop down here and go to contrasts. And if we, for looking at the effect of, that's right, for gender first, we have to go minus plus, minus plus. If I did that, well, a plus, minus, whatever it is, either way. Right, you see how that's actually tapping those categories. It's grouping the categories that are of the same gender to look at whether gender is really making an effect here. So if we hit done, we look at our F ratio 185 and our absurdly tiny p-value, we can go over here and compare that. And indeed, it is 185. right? And this is a 1 degree of freedom contrast, right? Just like our effect test here is a 1 degree of freedom effect test. It's actually 1 degree of freedom. It only takes 1 degree of freedom to test that. There's only one difference there. Now, second, we can actually look at the effect now of being a runner or not. So we'll call this, well, unfortunately, G is also there. So runner or control, why not? In that case, what we're looking for is the differences between individuals, regardless of gender, between runners and controls. So just -1, +1, -1, +1. Grouping the controls together with one contrast weight and grouping the runners together with another, right? So if we go to the drop-down, request another contrast, we can do it that way. And they're already organized for us that way, so we can just give the controls minuses, give the runners pluses. I don't know why it did that. There we go. Sometimes it gets exuberant and comes up with weird fractions. It shouldn't actually run if I don't know. It'll do something weird. And you can do contrasts that are weighted differently if you're trying to do special things about predicting when a population is of a different composition than yours. We'll get to that later. But this contrast, let's run. We have a huge F ratio and an even more absurd p-value. 110 decimal points to the left. But 695, and if we look over here, indeed that is our effect of group, right? So that's our effect of being either a runner or not. So we're getting completely comparable results here, which is good for us. Now the question is, how do we get that interaction contrast? And the trick is, and it's easy in this case because we only have 2 contrasts to do it with, the trick is just to multiply down, right? And that's going to give us a contrast that taps the interaction. Literally G times RC, or remember when we set it up with the contrast panel, or in the fit model panel, it's one factor times another factor. So you can just remember that's all you have to do with the contrasts that are tapping the group differences. You just multiply them down, and that'll give you a contrast that taps the interaction. So if we think about what that would be, -1 times -1, +1, negative times a positive, it's a negative, negative times a positive, a negative, positive times a positive is a positive. So this is actually our interaction, our G times RC interaction. So 1, -1, -1, +1. It's tapping the difference of the differences. Now another way you can think about this is if we were to write out these categories, so male C, male R, female C, female R, and we were to give them coefficients, right? So the difference between these two, let's say this is +1 and this is -1, right? And let's say these, +1, -1. And we want to find the difference of these two. So this contrast minus this. Notice what that's going to do. +1, then, what is that, still -1? Negative times a positive, it's going to be -1. And then, well, it didn't work at all. Oh, negative times, propagate that out, +1. So just expand it, and positive there. So if you want to think about it that way, it really is the difference of the differences that this contrast is tapping, right? And so if we do that, let's actually do one more contrast here. So we can just do negative, positive, positive, negative, or positive, negative, negative, positive, either way. And look at what that comes out with. So 7.40 and 0.006, and indeed that's exactly what our interaction term is there, right? So these effect tests are really just specified contrasts. What they're doing is weighting the means in such a way to detect the effects that fit into the category of either a main effect or an interaction effect. And again, interaction is just the difference of the differences, right? So if the difference of the differences are different, that means your factors are interacting. There's something different about being in one condition, or sorry, something different about a factor when you're in one condition versus the other factor or other level. Okay, so now that we've done this stuff, let's actually go back and pretend like we were actually running this analysis like proper scientists, and we checked our assumptions off the bat. Now, with our two-way ANOVA, we actually have, right, 4 groups that are made up of really differences in these 2 different columns. So if we were to try to do what we did before, let's actually save our residuals and give it a try. So if you go up to the top, save our columns and save our residuals. So if we try to do what we did before, right, which was to just plot the residuals by, let's do first the homogeneity of variance. So actually try to plot them against our group and gender. So if you put these in here, Now what fit y by x is going to do, rather than find the intersection of these or the interaction, the cells that make up the combination of these two, it's just going to do it separately for each group. So for the grouping variable, it's going to plot control against runners, and for the gender group, female against male. And so we could actually run our homogeneity of variance tests on these, go to unequal variances, and we can find out if our variances are differing within these ways of grouping our data. But really what our model is assuming is that the combination of the cells, all these different cells, have equal variances. Now they're pretty corresponding things. You're going to tend to find problems if you do it this way and if you do it the other way. But this isn't formally what we'd want to be looking at. We want to look at actually the combinations of the cells and see if the variances are equal. Essentially what we want is this fit y by x to have 4 levels here and see if those 4 levels have different variances. Does that essentially make sense why this is not quite what we want to be looking at? So the way to do that, which is pretty simple, is just using the concatenate feature in JMP's formulas. So what we want is essentially a new column that is going to be a combination of these two factors. That is, it's going to have a unique value for each person based on the different categories they're in. So we want a variable here that says control and female, and a variable down here that says control and male, or a cell that has control and male. And the easiest way, especially when we have labels here that are characters, is just to make a new column. We'll call this combined, or whatever you want. What I'm going to do is right-click on it and go to Formula. And so once we're in here, we have a lot of functions. Have I talked to you guys about character functions and formulas yet? Maybe only briefly. You can do a lot of really useful things with character functions. So if you're familiar with most programming languages, they have a lot of functions you can do with characters. You can concatenate, you can take characters from the left and the right, you can take midpoints. You can do lots of things. The simplest one is just concat. And what concat will do is take whatever 2 variables you give it, and for each row in the data set, just combine those 2, so squish them together. So we could actually just take group, select the other cell, gender, and what you'll see is going to happen is it's going to create this new column that has just the combined levels. And of course, each of these is representing a separate category. So when we actually put this now under Analyze and Fit Y by X, so when we put combined as our factor, it's going to have 4 different levels, 4 unique combinations of those 2 factors we had originally. And then we can look at the residual heart rate, now separated by those 4 different categories. So actually looking at them within each cell of our design, rather than looking at them collapsed over a different variable for each one. So now that we have that, we can just go to our unequal variances test and actually look if we have evidence that the variances are differing by group. In this case, we certainly do have evidence. So if you look at these p-values, we definitely have evidence that the groups are differing in their variances. Again, like all these tests, or like any statistical test, the more individuals we have, the more likely it is we can reject the null if there actually is some difference. But again, p-values aren't an indication of effect size. They're an indication of statistical significance, whether we have evidence that things are differing more than we would expect them to differ by chance for the given experimental situation, typically for how many subjects we have. So our p-values are small here, but if you look at our standard deviations, they're pretty close to each other. So 16, 17, 15, and 12. They're not differing by magnitudes of 2 or 3, or any magnitude, as we'll see tomorrow, that's really of concern. When they're this close together, so within 10% or 20% of each other, this is effectively equal variance for our purposes. For an analysis of variance, this is just fine. So despite the fact that we have differences that we can detect, that the variances are actually different. So for certain categories, individuals do differ more from each other. Specifically, the most different is the control males. So they're more variable than each other than any other category. And male runners are the least variable. Despite the fact that we know that that's truly a difference in the population, the difference is such that it's just not very large. We're able to detect it because we have huge numbers of people in our study, but the effect is just, or the difference is just not very big in terms of absolute terms. Okay, so we're able to look at now the homogeneity of variance. Important thing to look at. We also have to look at normality of these errors. Again, we can do this through our fit y by x if we want to do it all at once. It looks a bit messy, doesn't really give us a real clear view. Plus, we can't actually request those goodness of fit tests. So my recommendation would be to, after you check homogeneity of variance, make whatever decision you're going to make, close that out, go back into distribution now, And what we're going to do is split our file using that by section with our combined. So now it's going to split for every cell in our design. And what we're going to do is look at the residuals now split by that combined variable. So we're going to get 4 plots. And what we can do for these 4 plots is first just sort of gaze at them casually here. I would say hold down Command and get the normal quantile plots, and then also fit those continuous. Just might as well do them all at once here, and goodness it fit. All right, so I just got the quantiles, saved or fit a continuous distribution, and then requested under the fitted normal the goodness of fit test. And so we're going to look for each of our different individuals here, or combinations. So for the control females, everything looks fine. We actually, even with this many people, it looks like we're upholding our assumption of normality. These individuals are pretty normally distributed about their center. Same thing looks to be true for our control males, fairly normally distributed, or nicely normally distributed. Same thing for the runners, and same thing for the male runners, although we can see a slight perturbation there, but nothing evidently that we need to worry too much about. These are nicely behaved distributions. This is as normal as we'd probably expect to get with any real data. So that's actually very nice for us. And as is sometimes the case, or often the case with physiological things, they tend to be more normally distributed than some other processes, just because the differences amongst people that tend to change things like heart rate. There's so many different factors that are affecting that. Central limit theorem essentially is holding across individuals for us. We have different things that are all contributing to one output measure. So things like height, weight, these things tend to be nice and normal. Heart rate, physiological things. So in any case, from this, we've pretty much upheld our assumption of normality. We don't have to be concerned at all about it. And as I said, for the variances, even though we do have evidence that they did differ, the magnitude of their difference was such that it's probably trivial. It's not going to affect our analysis of variance in a substantial way. We'll see tomorrow again how substantial we need to be really concerned about. So we can close that. So now that we've looked at that, we can go back to our analysis and essentially be assured that our results here are not driven by some huge violation or something really bizarre. Right? We're able to really be certain of these differences. And again, even if we had made some small violations or detected some small violations, these results are very large, right? So an F's of 695, typically not something you would get in social science ever. But these effects, I don't think anyone would question you on if your assumptions were valid or leading to these things. One thing we haven't checked, of course, are the independence of observations. That is one thing that will seriously screw up an analysis of variance, and that just has to honestly be determined by your experimental method, looking at how you collected your data. And in this case, assuming these are all different individuals, right, we can be reasonably assured that these observations are independent. There aren't very good methods unless you have other information about these individuals that you can really check if they're independent. But in this case, we just have to be assured that when they collected these data, they were doing it in such a way that didn't violate that assumption, that we didn't get people who were, let's say, all from the same dorm room over and over, or we sampled in such a way that we got husbands and wives, people who might share eating habits or things like that. We're just hoping that these individuals are all different. Okay, so that's all we're going to do with the two-way. Is everyone fairly comfortable with that? We had a two-way analysis. You can check assumptions, interpret effects, come up with contrasts. Okay, so let's close that out. Now the next one we're going to take is route. So we saw this one before. These were these different routes to campus. And what I want to do with this set actually is what we just did over here. So creating those interaction terms using contrast, but do them for a little bit more complicated of a design. I don't want to jump all the way up to how complicated this is. This is a 3x4 design. So we have 3 levels of the first factor and 4 levels of the second. I want to take it actually down to a 2x3, just so that we can do it a little more simply. Everything generalizes. But if you remember what the effect looked like, so I'm going to just do this quickly. What we were looking at was, again, the effect of different routes to campus and the time it took. And what we found was that there was this, effect such that for La Jolla Village Drive especially, there was a major time effect, right? But for these other groups, so for Genesee and Gilman, there wasn't too much interesting happening. Let's imagine, for example, that we just wanted to do a sub-design here. We wanted to essentially eliminate Genesee and Gilman and just consider La Jolla Village Drive and Nobel, so 2 levels, and then for the 3 time points, so for 8 to 9 p.m., or 8, 8:30, and 9 a.m. So to do that, a simple way, let's just right-click on the route column and do sort. And what we're going to do is just exclude the cases that have to do with Genesee and Gilman. So if we start at the top, click 1, hold down Shift, and click down to 20. We can then right-click on those cells and select Exclude. And what that'll do for us is just exclude them from any analysis. It won't delete them out of our data set, but they won't be considered for pretty much anything we do. So essentially now what we're going to have is a design with 2 levels of one variable, 2 levels of route, and 3 levels of time. So if we refit this analysis now and go into Fit Model, select our 2 factors, and we could just do the full factorial. And again, we're trying to predict the time it takes. And again, it expands our parameter estimates. Go ahead and close that. If we do this, we're going to have, of course, different results, right? And we're only considering certain portions of the data. But we're going to be able to essentially build these interaction terms and the main effect terms using contrast in a little bit more complicated of a way than this was, right? Because we actually have for, remember, the time effect, a single contrast won't be able to capture all the differences in that variable. There are 3 levels, so we have to form 2 different contrasts that actually tap all the places where differences could occur. Route, we only have 2 levels, so there's still only 1 contrast, so C-1 in this case. And for time by route, since we now have the combination of a 3 and 2 level variable, there's now actually 2 contrasts we have to form that are going to tap the interaction, right? So if you think about what we did here, we just took the main effect interaction terms and multiplied them down, right? So if we have 2 that are going to tap, in this sense, route, or sorry, 2 that are going to tap time and 1 that taps route, we have 3, sorry, we have 2 first times, well, let me just draw it out and I'll stop screwing up. We're going to have an eraser. We'll have 2 terms that are actually going to tap the interaction, right? So we can build these out. And again, we're doing this not because we can't let JMP just do it for us, but mostly so when you have to do contrasts on your own that maybe are tapping specific subparts or subportions of your design, you can actually investigate interactions that are just smaller portions, not the overall interaction. Especially when we get into higher way designs, 4, 5, 6-way designs, where you have these 6-way interactions and these strange terms, you're going to actually be able to isolate parts of your data and say, you know, is the interaction at the higher level due to some specific lower level interaction? So having a handle on contrast is really quite helpful. Okay, so let me actually see how it nests these so I can write it up here, right? So it does time. Well, whatever. Let's just write it out like this. So again, we have 3 levels of time. Well, let's do it like that. So we'll do 8 o'clock. That's going to have 2 different routes. So we're going to do it like this. 8:30, 2 different routes, and then 9 o'clock, and 2 different routes. And essentially, we're thinking about this right now as a one-way design. If we actually were to create in our data set using concatenate those variables, we can do this analysis with that concatenated variable and just think about it as a one-way design. The nice thing about using this interaction panel for the contrast is it's essentially giving us the contrast selection as if it were just a one-way design. So let's go ahead and think about these. We have, what did we choose for this? La Jolla Village Drive and Nobel. So La Jolla Village Drive, Nobel, La Jolla Village Drive, Nobel, La Jolla Village Drive, and Nobel. And we're going to have 2 main effects that we're going to consider, and then we're going to have that interaction at the end. Let's draw this across. Get a better pen here. How about red? Sure. Okay, so let's first think about the contrast that would help us determine whether it's an effective route. Right? And we know there's only 2 levels of route, so we actually only have 1 contrast we have to write. So the effective route here. Do it like this. And so for our contrast, all we're doing is giving values again to La Jolla Village Drive and Nobel, just different values, regardless of what time they fall in. Essentially, we're just going to average over them. So quite simply, just 1 and -1 for each of these, or -1 and +1 if I say it like I wrote it. And that's our contrast, right, for the effect of, in this case, route. So if we run that in here, so we actually just give negatives and positives for each adjacent. Oops. Negative, positive, negative, positive, negative. You see it goes ahead and rescales everything for us quite nicely, so a third for each. And if we hit done, we get an F ratio of 17, and this small p-value, confirm that that is actually our effective route, and it is. Right, so that contrast is essentially a little detector we've built to detect differences that would pop up in route. So it's literally saying the average of the Hoya Village Drive in all the times versus the average of Nobel at all the different times. There's no other way those two routes can differ except for that place. Right, so that detector is sufficient to pick up all the differences. Okay, what about the effect now of time? Now time has 3 levels, 8, 830, and 9. Right, so we're actually going to need 2 contrasts to pick it up. So it's just the number of levels minus 1 is the number of contrasts you actually need to pick up that effect. Now when we get to 2 contrasts, we can actually do different types of contrasts to pick that up. We don't actually have to use just a 1 and -1. This is where we got into these polynomial contrasts, which are ways to essentially build a detector that picks up differences in more than 2 levels. Another simple way is just always having the last level be, well, let me write them out. So a simple way, and this is the one I usually do just because polynomial contrasts are usually only helpful if you have quantitative variables as your factor. Even though time is sort of quantitative, it's not in the same sense as like a dose level or something like that. So the easiest way to do this, and again, notice that what we're going to be doing implicitly is giving the 2 routes the same contrast weights. No matter what we do, they're going to get the same weights because we're averaging over them. So to pick up the difference of time, an easy way to do this is just give first the last level something like, well, let's see what the easiest way to do this is. That's not going to be weird. Let's do it like this. So -1, -1. Is that right? Now I've turned myself all around because I have it broken down like this. Well, it should just be -1, -1, 2. So we can just give these the same weights. There we go. So that's the first contrast. So the average of the first 2 versus the last. And then the second contrast is you just ignore the last category and give this as -1, -1, 1. And then this contrast weight is just going to be 0, as if it didn't occur. And so what this is doing, it looks strange when it's sprawled out over the other factors. But what it's doing is saying, first take the average of the first 2 groups versus the last, and then the average, or sorry, the difference between the first 2 groups. And that contrast, or those sets of contrasts together, which are orthogonal, they tap different things. Together, that set will partition the sums of squares associated with the time effect. And so in JMP, what you're going to see we have to do is test these simultaneously. We're going to tell it to group together the sums of squares that this contrast predicts and the sums of squares the second contrast predicts. Now we could have also, using those polynomial contrasts, first set the first contrast up as a linear contrast. So it'd be -1, 0, 1. And then the second as the quadratic contrast, -1s, a 2, and then -1s. And that would also pick up the same sums of squares collectively. Either way, we're really setting up these contrasts right now just to demonstrate that they pick up the same sums of squares as the main effect. But notice that there are different ways to do these as long as they're orthogonal. Okay, so we have the contrasts. Now let's see how we would enter them. So under your time by route dropdown, go to your contrast again. Let's start with the first contrast, so -1s for the 8 o'clock, no matter what route they're at, -1, no matter what route, and then +2 for the 9 o'clocks. So we can do, this is kind of interesting to enter it, so hit negative, 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 then positive, positive, and it should set it up for us that sums to, yes. Yeah, perfect. Right, so it's all the groups versus the last. Now you're not going to hit done yet because, right, we need to have 2 contrasts together that are tapping these. So we're going to hit new column. And this gives us the ability now to do a 2 degree of freedom contrast, a contrast that takes the sums of squares from two different contrasts. If they're not orthogonal, it'll let you run it. It's just the result may be a little bizarre. Typically, you only put together orthogonal contrasts in this 2-degree of freedom test or multi-degree of freedom test. But just notice that it's not going to give you an error if you don't. So be careful. So in this one, again, we're giving -1s to the 8 o'clock, regardless of time, and +1s to the 8:30. We're just going to ignore the last category. So in this case, we just do negative, negative, positive, positive, right? And so now we're just comparing the average of these groups to the average of these. And then now, if you hit done, it's going to compute for us the 2-degree of freedom, and it even says numerator degrees of freedom 2, and it gives you denominator degrees of freedom. And 8.20 should hopefully be, yes, our effective time. So 8.20 is detecting the same sums of squares, right? And the way we form these is just this rule that you can take the average of the first two versus the last, and then the second one is just the average of the first two. If we had 3 groups, we would actually have to have, if we had 4 groups, we'd actually have 3 contrasts. So the average of the first 3 versus the last, the average of the first 2 versus the third, and then the contrast of just the first 2. So you see how it steps down in that manner. Okay, so we're able to do time and route, now this interaction term. Notice it tells you over here degrees of freedom 2. That's going to exactly correspond. We need 2 contrasts to pick that up, right? So let's go ahead and get our panel set up first, and then figure out what we're going to enter. So we know we're going to have 2 contrasts, right? And the easy way, again, is if you have already your main effect contrast set up, you know your R times T, your route times time contrast, is just the product of your route times the first time contrast and your route times the second time contrast. So we just have to multiply them out and get whether they're positive or negative. So let's do it for this first route times the first time. So negative times a negative is a positive, negative times a positive, negative, or positive times a negative. Negative times a negative is positive, positive times a negative, negative. Now we have a 2, so a negative times a positive 2 is a negative 2, and a 1 times a 2 is a 2, right? That's our first interaction contrast. It's not going to tap everything. We have to actually tap the next set, which is now this route again times time, the second contrast. So negative times a negative now, positive, positive times a negative, negative, negative times a positive, negative, positive times a positive, positive, negative times a 0, 0, negative times a 0, 0. All right, so now we have our 2 interaction contrasts, which are orthogonal, and they're going to tap for us the complete set of ways that the differences in the differences can differ. Right? So again, remember contrasts that tap interactions are always looking at how different the differences are. These are just 2 contrasts that tap all the places where the differences could be different. And that's all they're really doing for you. It's just this trick makes it a lot simpler to organize them than trying to work those out in your head. So let's actually put these in. So we have a positive, then we have a negative, then we have a positive, then we have a negative, and then we have a negative 2, so hit negative twice, and then positive twice. There we go. And make sure these all line up. So we have positive, negative, positive, negative, negative, positive, with these being twice as large. Perfect. So don't hit done yet. Let's make a second column. Now we have positive, negative, negative, positive, and then just our zeros. And this may remind you of our contrast we had before, the difference of the differences, just the positive, negative, negative, positive when you have 2 levels. So go ahead and hit done. Let's make sure this worked. And we have F ratio of 12. Make sure it lines up. 12.5. Perfect. Right, so these are testing for us the same things that we did over here. So these would be contrasts you would frankly never set up. But imagine that we didn't exclude from our data set all these other columns. We could have done this exact contrast setup, these exact contrast setups, without ever having to exclude data. The benefit would be as well that we would have extra data to estimate the mean square error. So by sub-designing it and then doing the main effects over here, we're actually kind of hurting ourselves, especially if we think the variances are equal, then we want to test these effects within just, let's say, La Jolla Village Drive and Nobel for the different times. We may want to test the interaction and the main effects within just that subdesign while still giving ourselves credit for making those extra observations. This happens a lot when you want to test the interaction of just a small piece of your study, but you have tons of extra data. You might as well use that data to estimate the mean square error to get a better handle on what the variance in the population is without really having to do a lot of extra work. So you could do this section by hand, let's say, but in, for example, most other programs, they just don't make it this simple, right? So in this case, if you can get a handle on just thinking about your design as a one-way and mapping these out, you could have just put in these values and just left zeros everywhere else. So, implicit here is we also have Genesee and Gilman for all these different categories, and they're just set to 0 if we were to use the original data set without the exclusion. And if we were to do that, and actually we could, but it would take a long time and it's useless, what you would see is that our p-values would be smaller, right? So our actual statistical significance would be improved by the fact that we have better evidence or better precision on the estimate for sigma, and so our actual mean square error is going to be smaller, and our F ratio is by default then larger. Right? So if we had, let's say, marginal effects here, marginal in the sense now of being not quite statistically significant or close to the border, our test would be improved by having that extra data, right, actually in our data set. So in this sense, if you're just doing this to replicate the results in your panel over here, that's sort of silly. But remember that this is general and usable if you're trying to do specific comparisons within your own data set. And especially this interaction term, because this is the hardest thing in most programs to do for a sub-part of your design. So if you want to get the interaction of just a part of your design, the difference of the differences, most of the time in most programs you either have to do it through syntax, like in SPSS you can do specific contrast like this, but it has to be through syntax, or you just have to exclude a bunch of your data to get the program to do it for you, which is typically what people do. So they just exclude the data that doesn't fall into the little analytic part they're concerned with, and they end up kind of shooting themselves in the foot. Okay, so this is fairly clear, right? So this way of orthogonalizing and then taking the products, it's pretty straightforward. Again, it works if you had even larger numbers. So if we had 2 contrasts that tapped route, if we had, let's say, 3 levels, you would, of course, just take the product of all of them and have 4 interaction contrast. So 1 times the first, 1 times the second, second times the first, second times the second. So you'd have 4 contrasts that would tap the interaction. So it's just a matter of bookkeeping, making sure you actually multiply them right and that sort of thing. Okay. So finally, so we can close out of this. Also, by the way, if we wanted to investigate our assumptions, we could use that concatenate trick also in here. So we would just squish these columns together, and we'd be able to plot the residuals by it. We already looked at this data set before, so we don't have to do that here. But notice that would be something you can do. Now the last thing I want to do is open this persistence data set. So this is a 3-way ANOVA now, and show you a couple things here, especially how just annoying it is to interpret 3-way interactions and deal with looking at them. And JMP makes this simpler, to be sure, but there's some tricks that I come across that just make it even simpler to get it to produce plots that make it easy to interpret. I'm going to tell you a little bit about this. This is just crap I made up. But what it is, in my hypothetical situation here, is we have a bunch of children who are young, and we're measuring how long they persist on a task that can't be finished, because I'm sadistic. And so what I did for these hypothetical 96 children is I gave them either a puzzle that was a thought puzzle, so something they had to work out in their head, or a physical puzzle, so denoted here as a 1 in the task. I gave them different amounts of sugar to see, presumably, how that had an effect on their persistence, and I recorded what gender they were, so males or female. Now, notice that our columns here don't have labels, which makes it really annoying sometimes to look at plots. So just quickly, I want to point out, in case I haven't shown you before, how you can make labels for these. Now, one thing you could do, and I think I've shown you this before, is if you go to columns and recode, you can recode new values for a column, but maybe you want to keep the original data coding or something. You just want it to put values in instead of the 1s and the 0s. And the easiest way is just to go into column info, so right-click. Under column properties, go to value labels. And what you can do is just put in for whatever column you're in, so we're in gender here, put in a 1 and say, call that a female for me, and 0, call that a male. And notice that you can click ranges, so you can actually have a range be denoted something. This is a really convenient way to split your file. If you want, you could just say take the range from something to something and call that male. If there's, let's say, an androgyny scale that you measured, you could actually have anything above 7 as male and lower than 7 female, whatever you want. In this case, we just have discrete values, so we're just going to have it recode. So go ahead and hit OK. And notice that what it's going to do for us is basically change all of them to be male and female. But if you double click, it's still going to have that 1 and 0. Now, the nice way about this is if you're constantly adding data and the person entering your data is using 1s and 0s, you don't need to keep recoding the entire column. You can just add data, and any new data you put in will inherit the value labels that you've already pre-described. For sugar, we don't have to recode anything there. It's just milligrams, I guess, or maybe grams, I don't know. Let's do task here and actually give it value labels too. So go under column properties again and go to value labels. And in this case, a 0 was the, what was it in my little hypothetical? We're going to say it was the physical task. I hope that's what it was. Well, whatever. Doesn't really matter. And then this was a mental task, so a mental puzzle for 1. All right, so the nice thing about, again, doing the value labels is that now when you plot this, the graphs you have will actually have labels other than 0s and 1s. This is especially helpful if you have lots of factors that have the same numbers. So 0s and 1s are identifying task, in this case, and gender. It gets really weird to say, okay, the group 0, 0 versus 0, 1, and 1, 0 versus 1, 1. It's like, what? So these are helpful because it'll actually label everything for you. Okay. So let's go ahead and set up our model. We don't have to look at the distributions here. I want to make sure to have enough time to get through interpreting this. Of course, the thing that I would recommend is, check out the distributions of these variables. Make sure you have equivalent numbers or at least enough individuals in each collection of categories. But now we're doing a 3-way ANOVA, so we have these 3 factors, which you can just select, and then go to macros and select the full factorial. And notice this is going to produce for us not only the main effects, so gender, sugar, and task, but also the 2-way interactions, gender by sugar by task, sugar by task, and then the 3-way, the highest level interaction, the gender by sugar by task. And of course, these different interactions are tapping different things, right? The gender by sugar is saying, does the effect of sugar have the same effect for different genders? Does the gender by task, or the gender by task interaction says, does the effect of task, being mental or physical, have a different effect for the genders? The sugar by task is saying, well, does the effect of task have a different effect at different levels of sugar? Then there's this weird one that's sort of difficult when you first come across 3-way interactions to think about. The gender by sugar by task interaction is saying, does the interactions that occur at the lower level, are they different? So, for example, if, let's say, the effect of the interaction is always that the first variable exaggerates the effect of the second, you may not have a 3-way interaction. But, for example, for some of these, maybe it's the fact that the, well, let's just look at them, then it's a lot easier to describe. Differences of differences of differences that are different, statistically. Okay, throw persistence in there, because that's what we're trying to predict. And go ahead and hit run. And you'll see we've just magnified our parameter estimates, just minimize that. Don't need to look at that at all. So the first thing, aside from looking at our assumptions, which would be a good thing to do, but assuming that everything is well behaved and we have no reason to think the ANOVA is inappropriate, you want to start by looking at the highest level interaction first, because that's really going to qualify everything below it. And basically finding this higher level interaction, so we have a gender by sugar by task interaction, tells us that we need to think about, or at least investigate, how the different interactions below it are actually playing out. So why they're differing, or what's going on. Now the effects down here, some books say, never interpret your marginal effects or your main effects if you're not being specific once you have an interaction. That's not totally true. I mean, you can think about what they mean. They're just the average effect collapsed over everything else in your model. The point there, and this is why Mark makes the point not to call them main effects and why historically you never did, is that average effects can hide interesting things. So we see on average, right, that there's a gender effect. So one gender is on average persisting longer than the other. But if we know there's interactions, that may not be true in all cases. It may be true that if you average over task, they are, but maybe they're wildly different. So males actually persist much longer on one task than females, and the opposite is true for the other. So average effects sort of hide interesting things if you have interactions, which is typically why the dictum is to not interpret them. The better method is to say, well, interpret with care. Think about what they mean. Yes, they're an average effect. On average, they're higher, collapsing over other things, but there's probably more to the story, which is what those higher level interactions are telling you. Now, getting at this three-way interaction is actually a little complicated. So if we scroll all the way to the right, and we actually try to plot the three-way interaction, of course, it's not going to do it in 3 dimensions for us. It's going to do this rather unuseful plot. Now, what I would rather it do, which what SPSS will do, is just split up by whatever factor of your choice the interaction. So you can say, for each task, plot the gender by sugar interactions. We're going to actually learn how to do that in JMP. It just takes a little more work. But notice we can plot all the other interactions. So we can look at the sugar by task. We can look at the gender by task. We can request all of these and look at a lower level, at least what's going on, averaged over the other missing variable. But that's not going to be the most helpful for us to do. Now, I pointed this out before under the drop-down, under factor profiling, is that profiler. And this becomes more useful the more factors you have. This lets you really look at what's going on in your particular analysis. So let me just put this up higher so you can all see it. Drag it out. There we go. Now, again, let's think about what the three-way interaction is. So if we click on any of these, we can quickly see two-way interactions really nicely. So for males, we can see what the effect of sugar is, right? Basically, more sugar means that they do worse or they persist less, which I think in my head that made sense. They get all ramped up. For females, however, more sugar helps them on average, right? So they actually do better, or they persist longer. Not really better, since none of them can finish anyway. We could also look at the effect at different levels of sugar. So we can say at no sugar, the physical task for males is the same. At 20 milligrams, the physical task is they persist less long than the mental task. And at 40, they persist even less of the physical task than the mental. And then we could switch over to females and say, okay, at 0, they do better at the mental task than the physical or persist longer. At 20, there's really no difference. And at 40, there's really no difference. Right, so implicitly, what I actually just did was show you what the three-way interaction was. You just have to hold a lot of crap in your head. So let me try this again. So at the level of female here, I want you to observe what the effect is of task. So at 0, for females that is, at 0 milligrams of sugar, or grams of sugar, they do better at the mental task, right? And then at 20 and 40, they do about the same. So that's the two-way interaction for females. Now let's look at that two-way interaction between sugar and task for males. Males at 0 milligrams do about the same at the physical task, which is different from the females, right? But then at 20 and 40, the difference between tasks gets larger and larger. Right? So the effect here is essentially that the effect of sugar, right, is to make the mental task easier for males, but really not do much for females. In fact, it levels out for sugar. So the effect of sugar becomes nothing on the physical task difference versus mental task. And I can show that again if we go to females. Basically, after a little bit of sugar, it drops off. And then for males, the effect only gets larger with sugar. So it's essentially aggravating or increasing the task effect for males as you increase sugar. But for females, it's depleting the task difference. Right? So three-way interaction. It's the interaction of the two-way interactions. Now, once you track down those differences, you can do the simple effect test to actually see if you're making true statements. So what I would do, right, for males, you'd want to do the simple effect test at each level of sugar and show that by the time you get to 40, that's a real difference. They're actually increasing. Whereas for females, you could show that the effect is non-statistically significant at all these levels. Maybe it's effective there. Now what that means, of course, who knows? I just made these data up. But at the very least, this profiler gives you a real quick way to sort of investigate how changes make changes for other factors. Now the plot that I was talking about, the one that SPSS does more simply, is if we could just get the two variable plot at the same time for males and females. So if we could just look side by side at the sort of effect of sugar and task for males, and then a separate plot right next to it for females. Now there's an easy way to do that. It may not be immediately obvious, but what you can do is go back to your fit model, take everything out, and now pretend like gender is a split variable. We're going to stick it in the by section. So what this is going to do is actually perform the analysis without that as a factor. It's just going to split the file. And then we're going to give sugar and task the full factorial. So I'm just going to select them and do the macro and full factorial. And so when I hit run here, again, gender is just your by variable. When I hit run, I'm going to minimize everything so you can see, I actually have two different analyses. Response persistence ANOVA for males and one for females. And so if I minimize a bunch of crap here, and then let's minimize this and this, and what I'm going to request is for the first analysis for the males, I'm going to request that plot of the effect, right? So this is the interaction of sugar and task. And then now for the females, do the same thing. I'm just going to minimize everything I'm not interested in and request the plot here. You can get an idea of what this three-way interaction really is, where the effect is cropping up. Right, in this sense, what you're able to see is, actually, let me plot them a different way. So I told you guys this last time. If you hold down Shift, it'll switch the axes it plots. So I want actually sugar, because it's a quantitative-ish measure, 0, 20, 40, greater is larger. It plots out on the x-axis, which is usually more intuitive for me anyway, than having something like task. Especially if you have 3 levels versus 2 levels, put the factor with more levels on the x-axis. It's usually more intuitive. Let's do the same thing for the upper one. So I'm going to take the plot away, go ahead and request it again. Here we go. So now this may give us a better way to sort of look at that interaction, right? So again, we're looking at the effect of sugar. So as sugar increases, how their persistence is affected, right? And we're looking at the top for males and for females in the bottom. So let's first look at males, right? So for the mental task, more sugar helps them. For the physical task, more sugar hurts them. They persist less long. And I think when I made these data, I figured, okay, well, so maybe the physical task, they're just so ramped up, they just give up because they're wild and boys are like that. Right? And so maybe for the mental task, they get better at concentrating. I don't know. I made up the data. It can be my own explanation. For females, however, we have a different pattern, right? So basically, we're seeing that for the mental and physical task, there's really no difference, except for at this one point, so at sugar of 0. There's this difference of task, but essentially that difference disappears. This is what we saw when we did the profiler. Basically, as we gave them sugar, the difference between the physical and the mental task disappeared. And so this three-way interaction is telling us that we have evidence that these two-way interactions, the interaction between task and sugar, is different for these two groups, right? And it's driven by a lot of different points, and that's always the challenge with three-way interactions, is how do you describe what that means? But essentially what you would do is come up with some story or think about what it is that this would imply about the construct. Maybe it's that mental and physical tasks are essentially the same for girls once they're a little bit sugared, whereas for guys they're different, when they are. I don't know. There's got to be some good explanation for fake data. But plotting it this way, again, is a great way to get these plots, but I want to caution you to not really look at the rest of the data, because you're sub-designing, right? So now we're doing this effect test, we're doing this analysis looking just within males, and the same thing is true for the analysis down here. We're looking at the effect just within females, which is fine. It's a fine way to break down your analysis, but you lose some data by doing it that way. You lose the benefit of all the additional subjects you ran in each one. But if it helps you get some clarity on what you're looking at, that's fine. But essentially what we're doing here is just breaking them apart so we can get these plots, right? And we could do this using the graph builder too, if you really wanted to get fancy. The graph builder, which I haven't talked to you much about, is fun. You can just drag things, so you can put persistence on the y. We can, let's not wrap, but group, sure. And then sugar we can make as the overlay or something, and then task as the, I don't know, there's some way to get this to work. Oh, no. We want to do sugar as the x-axis here. And then we can actually change these points to bars. It's not that pretty, but there are ways to make it work using this as well. But I would recommend, if you're just trying to get these plots, just let JMP do it for you. It's quick to get it done this way, and then you can really visualize these. But right, so on top of, the main point here, I would say, is with three-way interactions, just spend some time getting to know really what your data are telling you. Oh, that's strange. Oh, because I have it in here. Here we go. Very nice bit. And that profiler is really helpful, I think, because you can really step through each of your factors and see really what it changes for your other factors. And especially for the two-way interactions, this is really helpful because you can see right away that for physical tasks, there's some effect of sugar here for males, and for mental tasks, there's this opposite effect, right? This almost crossover. And you can just visualize that quickly. Now, a tool that I don't find particularly helpful, but some people do, is this interaction plots, which produces in a pretty ugly way. I'm not sure why it's so ugly. That's way too big. There we go. It produces the two-way interactions for every combination. So gender by sugar, then sugar by task, and it does them with both axes. So what's kind of nice about this is you can see it plotted with gender as separate lines here, or as sugar as separate lines. So you can sort of vision these two interactions in both ways really quickly. But it's just so ugly, I don't like to use it. So I don't want to let that be a reason not to use it. Just know that it's there if you want to quickly look at all your two-way interactions really quickly. It gives you the ability to look at those, break them down. But again, this isn't really giving you information about three-way interactions, because to do that, you have to split essentially based on another factor. Because you're looking at two-way interactions only within one factor, or one level of one factor, or the other level. Or if you have multiple levels, within every single level. So I also bring this up to caution you when you run analyses or design experiments. When you start putting in 4, 5, 6 factors that you're trying to consider, and then you get one of these incredibly high-level interactions, it gets incredibly difficult to track down. So simplicity is the word here. I mean, if you can do a study and not have 7 factors, that's great. If you have to have them, that's of course fine, but make sure you're prepared to really investigate all of these things, because you really have to, especially if you have one of these interactions really high up, you really have to start thinking what that's telling you about your data. And essentially, it eventually will break down to probably you just splitting your file or looking at specific subparts of your data to see what is interesting. But I'll make this point, which is that there's probably no social, psychological, or any, let's say, any social construct where you would predict a 5-way interaction, and that is telling you something interesting. I mean, maybe you would predict certain comparisons, but you can probably write any of your sort of relevant analyses in terms of simpler contrasts. I don't think there's any study where you would say, this theory predicts specifically this 5-way interaction with these factors. Usually it's, this group should be different from this one, and maybe this one from this one, and maybe that difference is larger. That's the sort of range of 2-way interactions, maybe 3 ways. But I don't know what sort of theory would ever predict something as crazy as like a 5-way interaction specifically. So that being said, you can handle them. Just be prepared to sort of investigate a lot of little pieces of your design in order to track down what's really going on. All right, that's all I got for you tonight. Any questions about, I guess in this case, the 3-way interactions and the 3-way ANOVAs? Everything else, of course, was the same. The analysis looked the same. Checking for assumptions is going to be the same. Really, the only thing that happens is this sort of increasing number of tests that are being run. And of course, we could come up with contrasts that would tap that 3-way interaction, right? So we could go through here and form all the contrasts that would actually make that up. We know that there would only be actually 2 of them, which is nice, but we'd have to figure out what they are. Yeah, we could do it.
So would you do that by kind of multiplying out the single contrast to get all the 2 ways, and then multiplying all those out to get the 3 ways?
To get a 3-way, yeah, I think you'd have to do that. So you'd have your 2 ways. Yeah, no, that couldn't work. You have to. There's some extra thing you have to do. I'm blanking on right now. I don't even know if there's a great trick for that. If it works for 2-way interactions, what's the trick for 3-way interactions? Well, I'll think about it and get back to you. What's that? Yeah, that's the trick. Just let the program do its job. Yeah, there's a trick for it, but I'm blanking on it right now. But yes, you could do it. Again, that's probably silly. So. All right. So if there's no other questions, I'll stick around. But otherwise, I'll see you guys tomorrow.